Hey everybody, this is 2006. So we have a small block of mass m is released from rest at the top of a curved frictionless ramp as shown above. The block slides down the ramp and is moving at speed 3.5 v0 when it collides with a larger block of mass 1.5 m. 3.5 v0, come on guys, why can't it just be v0? Anyway, at rest at the bottom of the incline, the larger block moves to the right with a speed of 2 v0 immediately after the collision. Express your answers to the following questions in terms of the given quantities and fundamental constants. First, determine the height h of the ramp from which the small block was released. So that always, when something goes down a ramp that's frictionless, that is conservation of energy. So we had gravitational potential energy, and that was going to become kinetic energy there. So let's substitute in for each of those. Generically, this is mass times gravity times the change in y position, and this is 1/2 times mass times the velocity squared. The masses will cancel out on each side here. We already know the velocity. We're looking for the height. Let's write that as h now, because that's what they want us to write it as. So it will be v squared over 2g, but that v is generic, so we have to plug in for the actual v that they gave us, and that v was 3.5 v0. So 3.5 v0 squared over 2g. So that is your answer to the first one, and you could work that out and square the 3.5 if you want. They'd also just take it if you left it like that as well. So, conservation of energy as it slides down there. The next part here, let's move that off and get this here. So they say determine the speed of the small block after the collision. So collision problems are always conservation of momentum. We know that the momentum of the system before is equal to the momentum of the system afterwards. Well, the only thing moving before was block 1. So the momentum of block 1 before is equal to the momentum of block 1 afterwards, plus the momentum of block 2 afterwards. Now we can start to substitute in for these. This will be block 1's mass times its initial velocity. So its mass is just m, the one up on the plane, and remember they said it came down and was going 3.5 v0 as it hit the bottom there. And then on the other side, the small mass is what they're asking for, its new velocity. So there's the small block's momentum afterwards, and the large block, it's got a mass of 1.5 m, and they say it moves off with a speed of 2 v0. So now we got to just do some algebra to solve for this. I will cancel the m's everywhere there. Let's fix this right here and see that now if we simplify it, we get 3.5 v0 is equal to v prime plus 2 times 1.5 is 3. So there we get 3 v0. So subtract your v0 to the other side. So 3.5 v0 minus 3 v0, and we get 0.5 v0 is equal to v prime. And so that's your answer. The small block has got to be going to 0.5 v0 there. Now, they have the larger block slides a distance d before coming to a rest. Determine the value of the coefficient of kinetic friction mu between the larger block and the surface on which it slides. This is a work energy theorem problem. When you see something sliding a certain distance and they're asking about mu, it's always a work energy theorem problem. So let's write that out. Work is equal to the change in kinetic energy. Let's plug in for those. So work is going to be force times distance. I'll go ahead and write a big D because that's what they said it is there, times the cosine of the angle between the two. And that will equal 1/2 times mass times velocity squared. I'm keeping it generic for now, so just a general equation. By the way, this actually I should have here a negative because the change is going to be whatever kinetic energy we had to begin with, we lost all that kinetic energy. So it is a negative. So the final will be 0 minus the initial kinetic energy. Now we can start to plug in for some of these values here. So the force is the force of friction that slows it down. So that's going to be mu times the normal force for anything sitting on a flat surface. And the cosine of the angle, by the way, it's going to be cosine of 180 because as it slides this way, friction will be back that way. I'm not gonna, well here, let's go ahead. Minus 1/2 mv squared. Let's substitute in for the normal force there. So the normal force is gonna be equal to, on a flat surface, mg, the weight. So mu times mg is the normal force, and I'm just gonna write the cosine of 180 as a negative, because cosine of 180 is -1. And that will equal negative 1/2 mv squared. Again, it's generic, I haven't plugged in for anything. The masses don't actually matter because they cancel out as they do in all skid problems. So those will cancel out. And now let's start to plug in. Oh, and the halves cancel out as well. Or sorry, not the halves. The negatives there cancel out as well. So we get mu times g is equal to 1/2. And now we should finally plug in that velocity that they said it slides off with. So the smaller block there slides off with the velocity, remember they said, of 2v0. And all of that gets squared. So then when we go to solve for this mu here, whoops, I left off something. Mr. Frankenhoff, there should be a d here and a d here. I left off the distance. So the distance is there, the distance is there, and the distance is there. I'm like, where's the thing I'm solving for? So when we go to solve for the mu there, we get mu is equal to 2 squared is 4 times 1/2 is 2. So we get 2v0 squared. And then we're going to divide by g and d there. So that is our coefficient of friction. Last part here is they say, let me find it, here we go. Indicate whether the collision between the two blocks is elastic or inelastic. Now you might think there's a tendency to want to say they bounced, so it is elastic. But inelastic may involve a bounce. So if you don't know, you've got to check. So let's find the kinetic energy before. That will be 1/2 times the mass m was coming down there, and it was going, remember, speed 3.5 v0, and you got to square that. So that was the kinetic energy of the object before. Then you got to look at the kinetic energy of both objects afterwards. We have the small block, again moving 1/2 m, and now it's going 0.5 v0, and you square that. And then the larger block also has kinetic energy. It will be 1/2. Its mass is 1.5 m, and afterwards it was going 2 v0 squared. So when you go to work these out here, you have to compare this amount of energy in this case and compare each of them here. And if you do all that, you'll actually realize that there is less energy in this case than there is in here. You can actually work it out and check it, right? The v0 squares are in each one, the halves are in each one. So really what you need to pay attention to is the numbers inside the parentheses there. So 3.5 squared, compare that over here to 0.5 squared, and here you get 4 from the square there, and multiply that by 1.5, and so 4 times 1.5 is 6, and so you're really comparing those numbers there. So 0.5 squared will get smaller, add it to 0.5, add it to the 6. I can already see that's going to be bigger than 9. So this side is less than that side, so our change in kinetic energy is negative. In other words, we lost energy, so it was inelastic.